Okay, so we have a question here. A customer has a budget of 500 kwacha and consumes two goods, apples and bananas. The price of an apple is 10 kwacha and the price of a banana is 5 kwacha. The consumer's utility function is given by UAB. Let me write it properly here. UAB equals A to the power 0.5, B to the power 0.5. So first, before we go further, I'll pose this question. Colleagues, in microeconomics, what is utility? When you hear the word utility, what comes to mind? Mm-hmm. Yes, Madam Christian? Yes. Utility is satisfaction. Okay. So with this utility function, it's showing the satisfaction that we get from consuming good A and good B. This topic is under consumer theory. Okay, we're trying to analyze consumer behavior. Remember, economics is all about making decisions with limited resources. Okay, so in this question here, this is on budget constraint. Okay, your limited resource is this 500 kwacha. Okay, and you can only consume two goods, A and B. All right. So we're trying to find out for this consumer, how many units of good A and good B does this consumer need to have so that they get the maximum satisfaction? Okay, colleagues, here we're trying to find out about maximizing satisfaction. Okay, there are different combinations of good A and good B that this consumer can have. All right, but we want the combination that will give us the maximum satisfaction. Okay. So, part A of the question is write down the consumer's budget constraint and set up the Lagragian function to maximize utility. Okay, so first we form the budget constraint. Okay, the budget equation. Let's record them at bundles. Let's record Sorry, my bundles are finished. Let's continue where we left off. Oh, Madam Christine, is that a question? I've seen your hand is still raised. Okay, okay. Yes, so we have to form the budget constraint, okay? The equation for the budget constraint. So remember, an equation for the budget constraint is y equals the amount of good A multiplied by the price of good A plus the amount of good B multiplied by the price of good B. Y represents your income. Represents the quantity of good A, which is apples in this case. B represents the quantity of good B. PA represents the price of apples. PB represents the price of bananas. So we've been given that question, that information here. The price of an apple is 10 kwacha. The price of a banana is 5 kwacha. So in our budget constraint equation, Y, the amount of money we have is 500 kwacha. A, we haven't been given A yet. Price of good A, price of apples is 10 kwacha. So we'll put here 10A. Okay. Then the price of bananas is 5 kwacha. So we're going to put 5B here. So this is our budget constraint equation. Any questions? Okay, now we have to set up the Lagragian function, okay, because this Lagragian function is going to help us determine how many units of good A and good B that we need to consume so that we maximize utility. Because remember here, as I said again, the main point of this question is we want to find for this certain person here, how many apples and bananas should this person buy so that they are very happy, very satisfied, okay, with this 500 kwacha which they spent. Okay, so we now set up the Lagragian function. Okay, first thing you need to do when you're setting up your Lagragian function is equate your constraint equation to 0. Let me type it here. We equate the constraint equation to 0. Okay, so our budget equation is this one. 500 equals 10A plus 5B. We need to equate it to 0. So basically, we need to bring this 500 over to the other side. Okay, so here on our left-hand side, we're going to remain with 0. Then we're going to have 10A plus 5B minus 500. Okay, equate your budget constraint equation to 0. After you equate it to 0, add, attach the Lagragian multiplier to this same equation. The Lagragian multiplier is shown as lambda. Okay, so we're going to multiply this whole equation with lambda. So we're going to say lambda, open brackets, 10a plus 5b minus 500. Okay, we distribute it out. Lambda times 10a, we're going to get 10a lambda plus lambda times 5b, we're going to get 5b lambda, and then lambda times negative 500, we're going to get negative 500 lambda. Okay, let's equate the budget constraint to 0, then attach lambda, the Lagragian multiplier. Then after I've done that, you can now form the Lagragian function. Okay, and the Lagragian function is just the utility function plus this function that we've got here, basically. Okay, so our Lagragian function is going to be L equals our utility function, remember, a to the power 0.5, b to the power 0.5, plus 10a lambda plus 5b lambda minus 500 lambda. Any questions? Where there? That's the it represents Lagragian function. Yes. Utility function. Remember this. The Lagragian function is going to be your utility function, which was given to us. This a b to the power 0.5. Then also it's also going to include your budget constraint equation. Okay. The Lagragian function always has the utility function and the budget constraint function. Okay. Yes. Uh-huh. Someone raise their hand. Yes. Okay, so we're done with part A. B. Derive the optimal consumption function AB that maximizes utility. So basically, we need to find out how many units of apples we need and how many bananas we need so that we are satisfied. So this is where now the calculus comes in. You're going to apply partial, this Lagragian function, you're going to derive it partially. Okay. So we're going to apply partial differentiation here. So the secret with partial differentiation is whatever is at the denominator is what is being derived. And if any term in that equation doesn't have what's in the denominator, it disappears, which I'm going to show you here. Okay, because maths is easier shown than said. Okay, so after you form the Lagragian function, next you need to partially derive it. So at first, we'll partially derive the Lagragian function with respect to A. So as I said, if any term in this equation doesn't have an A, it is going to disappear. Okay, because A is the variable we're deriving here. Okay, so if anything doesn't have an A, it disappears. Okay, so this is how we're going to derive. Okay, so here we've got an A to the power 0.5. So remember, colleagues, differentiation, multiply the exponent with the coefficient. 0.5 times 1, you get 0.5. 0.5 minus 1, you get negative 0.5. So we're going to have 0.5a to the power negative 0.5. Any questions, colleagues? This b remains as it is. Okay, since the a and b are attached, so the b doesn't disappear. Okay, if it was a plus b, the b would have disappeared. But whenever variables are attached, you leave the other variable. So this b will just remain b to the power 0.5. Okay, so we've derived the first term here, this one. Okay, it has given us this here. Then we go to the next term here. This 10a lambda, it has got an a, so we derive. So you're going to say plus this 8 to the power 1. So remember, with differentiation, 1 times 10, you're going to get 10. Okay, then 1 minus 1, always subtract a 1 from the exponent. 1 minus 1, that is 0. So a to the power 0 is the same as 1, so you don't need to show it, okay, colleagues? A to the power 0 is the same as 1. This is from laws of indices, okay? So here we remain with 10 lambda. Any questions before I proceed further? This 5b doesn't have an a, so it disappears. This 500 doesn't have an a, so it disappears. Okay, so we've derived our Lagragian function partially with respect to a. And after you derive, okay, you're going to form an equation, okay, where lambda, you're going to take it over the equal sign. Okay, you equate this to 0, then it becomes 0.5 a to the power negative 0.5 b to the power 0.5. Okay, this 10 lambda will go over the equal sign, so it's going to be minus negative 10 lambda. And you label this as equation 1. So with partial differentiation, you look at the denominator. You see, if any term in the equation doesn't have what's in the denominator, that term is going to go. Okay. We're going to derive again our Lagragian function, now this time with respect to b. Meaning, if any term in this equation doesn't have a b, it's going to disappear. Okay. So let me erase this here first. Okay, so we look at our Lagragian function again. Okay, so here we've got a b. This a will remain the same. Okay, a to the power 0.5. Then b, we're going to differentiate. So you say 0.5 times 1. Okay, or since both of these are attached, so basically times 1, it is 0.5. So you put here 0.5 here. Then you subtract the 1 from this. 0.5 minus 1, you get negative 0.5. Ten a lambda doesn't have a b, it goes away. 5b lambda, there is a b here. So this b to the power 1, 1 times 5, you're going to get 5. And you subtract a 1 from that b, 1 minus 1, 0. So b to the power 0 is the same as 1. So it disappears, and you remain with 5 lambda here. Then we equate this to 0. negative 5 lambda. And you write this as your equation 2. Third, we're going to partially differentiate our Lagragian function, this time with respect to lambda. Meaning where there is no lambda, the number or the term disappears. So just do this. Okay, so a to the power 0.5, b to the power 0.5, it doesn't have a lambda, so it goes. 10a lambda, we have a lambda here, so this lambda is like lambda to the power 1. 1 times 10, that gives us 10a. Okay, because when you subtract 1 from this one, 1 minus 1, we have lambda to the power 0. Lambda to the power 0 is 1, so it goes away. The next term is 5b. Okay, so here we have lambda to the power 1. 1 times 5, we get 5b. We subtract 1 minus 1, that is 0. Lambda to the power 0 is 1. Minus 500. Okay, 500 has got a lambda. Lambda to the power 1 times 500, you get 500. Okay, then you equate this to 0. And then basically you're getting your budget constraint function again. 10a plus 5b equals 500. Any questions? Remember, colleagues, I'm very flexible, so you can, where you're lost, let me know. Okay, don't remain quiet. And then when we've reached the end of the as we move further, you're just getting more confused to the point where now you are just totally lost. So I'll walk through the names first to see. We'll start with, yes, Madam Christine. Any questions? Madam Lynn? Mr. Francis? Mr. Moses? Mr. Izemba? Mr. Chisanga, Mr. Gilbert. Okay, so these Lagragian functions, they are used when you're just trying to find the maximum satisfaction, or other times you can also use it if you want to find maximum output. They're usually for maximization problems. So once we've got all these equations here, okay, okay, the next step is to equate equation 1 with equation 2, okay. If you want to make your life easy, just you can just say divide equation 1 by equation 2. Okay, because when you do when they do the equating part, you have to do more tabulations. I mean, you have to there'll be a lot of rearrangements that you're going to need to do with the function. Okay, so in the exam, you won't have all that type. Okay, so you can just say divide equation 1 with equation 2. Okay, equation 1, we had 0.5 a to the power negative 0.5 b to the power 0.5 equals negative 10 lambda. Yes, that's what I always do. All of my classes, okay, every class of mine, I record. Because these things, you need to watch also at your free time. Maybe here you're busy with something, okay, so you need to watch at your free time. So, sir, don't worry, okay, you'll be covered for, okay. Yeah, yes. So on the right hand side, these lambdas cancel each other. Negative 10 divided by negative 5, you're going to get 2. On the left hand side, this 0.5 and this 0.5 cancel each other. Okay. Now, these a's, okay, remember laws of indices. If you are dividing, what happens to the exponents, colleagues? If you are dividing, you see those who remember mathematics. If you are dividing two terms with exponents, how will you treat the exponents? you subtract. Thank you, thank you. I was even about to say, but thank you, okay? So this a, okay, it's like a to the power negative 0.5 minus the 0.5 down here. Okay, and we are subtracting this negative 0.5 here, and this negatives and this positive 0.5 for A. Then for B, it is this positive 0.5 minus negative 0.5. Okay. So negative 0.5 minus 0.5, you get negative 1. So you have A to the power negative 1. 0.5 minus negative 0.5, negative and negative make positive. 0.5 plus 0.5, that is 1. B to the power 1 equals 2. Any questions? Then, since this is a negative power, we get its reciprocal. Remember, indices again, a to the power negative 1 is the same as 1 over a to the power 1. Okay, so we're going to have b over a equals 2. We cross multiply. Okay, I want to make one of these letters the subject of the formula. Okay, so we cross multiply. B times 1, that is b. A times 2, that is 2a. Any questions? Okay, no questions. Wonderful, wonderful, wonderful. Okay, so now we can substitute, because remember, I want to find the number of apples and the number of bananas. Okay, I want to find number of apples and bananas. So this b equals 2a. We can substitute it into this equation here. Okay, our original budget constraint equation, 10a plus 5b equals 500. Yes, where there's b, substitute b with 2a. Okay, so if we do that, 10 plus, or 10a, 10a plus 5b So the B, this B we substitute it with 2A, okay, because B equals 2A. Equals 500. 5 times 2A, that is 10A. So of 10A plus 10A equals 500. 10A plus 10A, that is 20A. 20A equals 500. So to get our value of A, we divide both sides by 20. Each people joining in late. This question is a, it needs a from the start. Yes. So 500 divided by 20, we get 25. Okay, so this person, to get maximum satisfaction, they need to get 25 apples. Now we also need to know how many bananas does he also need to get. Okay. So here, since we've already got B equals 2A, and we know the value of A. So you're going to say B equals 2, A equals 25. So 2 times 25, that is 50. Okay. So B should equal 50. Okay. And if you substitute this back into the original constraint equation, okay, 10 times A is 25. 10 times 25, you get 250. Plus B is 25. 5 times, B is 50. 5 times 50, 250. 250 plus 250, 500 kwacha. Okay, so for this person to be maximally satisfied, they need to get 25 apples, they need to get 50 bananas. And that way they will satisfy, they'll get the maximum utility, which is the maximum satisfaction.